can make it very cheap to compute, like 63 times cheaper compared to the most efficient Solidity code right now. So I would say it's one of, if not the lowest hanging fruit we can implement today to speed up the EVM, as in the computation, not state access. State access is the main bottleneck, but for the computation part, I think CLZ is one of the lowest hanging fruits. And this actually has an advantage, like this convention makes some operations like string searching easier. I will argue that it's more than 63 times cheaper. And of course you get a smaller bytecode.
Hello everyone and welcome to PEEPanEIP, the series where we unpack Ethereum improvement proposal with people who are shaping Ethereum's future. This is episode 153 brought to you by ECH Institute. I'm your host Pooja Ranjan and I'm joined by my colleagues Valeen and Akash. Today we are diving into EIP-7939, which proposes a new opcode CLZ, count leading zero. Documented in April 2025, this is a standard stack core EIP, currently in draft status and SFI'd for Fusaka network upgrade. The proposal is co-authored by Vectorized, Georgios, Johan, Ben Adams, and Julio. Joining us today is one of the co-authors, Vectorized, to walk us through the importance of this opcode, how it can reduce compute and proof cost, and what we can expect from it in the upcoming Fusaka upgrade. Welcome, Vectorized.
Okay, good morning everyone.
Could you tell us a bit about yourself, your professional background, how you found Ethereum, and what are you currently working on?
Okay, so my main project, which most people know me for, is solady.org. You can visit solady.org. So it's like a library of Solidity snippets. It's a very highly guess optimized library. So most of it is written in inline assembly because we want to really make things fast and cheap and small. And yes, some cool cutting edge features. A bit experimental, but we do our testing very vigorously. Solady is free open source software. But to make money into it, I work for Ithaca. So Ithaca, which is a Paradigm Popco, they are trying to make some accounts, and they are also they also maintain Ref, which is one of the most popular L2 clients. Another job is I work at clusters.xyz, which is kind of like a multi-chain identity system. They also maintain like delegate cache and other utilities. Yep. So most of my work can be overlapping, and Solady is in the middle of the overlaps. And because in Solady I have so many occurrences where I have to do this count leading zeros, I would say sub procedure, I decided like why not just make an opcode for it. And how did I come into Ethereum? This is a story I have to tell everyone every time. The long story short is there was one of my friends, I think he's like a product lead at Mentor right now. He's called Joshua Cheung. He went to the same university as me, and he was like, you are so into all this optimizing stuff. You spend so much time optimizing weird useless stuff in your university. We are such a perfect fit for Ethereum because everything is metered to the opcode level. You have to optimize everything. So I was very skeptical. Then one day, somehow, I was requested to make an NFT project, and I was somehow have requested to learn Solidity. So
interesting backstory. We love to hear these backstories because it always connects us from the community, and we know that any developer and every developer is coming from community itself. Thank you for sharing it with us. Well, we want to make this EIP easy to understand for the broader Ethereum ecosystem. And the goal here is to explain what it does, why it matters in a way that people understand what to expect with the upcoming upgrade. We hope this episode helps simplify the concept for everyone. So without further ado, let's peep in.
Okay, let's go. So EIP-7939, leading zeros. CLZ. This is a opcode that you can find in most modern processors like your Apple M4 chip, your Intel latest chips, your Ryzen's. I think most of them have CLZ because it's such a important bitwise operation. But the EVM doesn't have it yet. So upcoming Fusaka hard fork hope it gets in and the adoption will be fast. So what is count leading zeros? What does it do? So you have a number. It can be maybe 32, 64 bit, but for the EVM, we are using 256 bits. So CLZ in the EVM, it will count the binary zeros. This is in binary format. So assume that this is a 256 bit number in binary form. Start from the most significant bit and count the number of consecutive zeros. So for this example, the count leading zeros is 3. And we have a special case. Say the number is 0. For the EVM, we define the result as 256. So this is to keep in convention with CLZ on like modern chips. So if you use CLZ on modern chips, if it's 64 bit, it will return 64. If the CLZ is 32 bit, it will return 32. Yeah, so we are trying to keep in convention with what processors have implemented. And this actually has an advantage, like this convention makes some operations like string searching easier. Okay, so there are some identities for CLZ. So for 256 bits, so to compute log2, the base 2 logarithm of a number x, you just take 255 minus CLZ x. So we don't need a log2 opcode because it's very simple to get log2 from a CLZ. CTZ is also very simple. You just take 255 minus this down here. It's basically isolating the least significant bit. So it's quite trivial to get CTZ. So you can get log2, you can get count trailing zeros. So for count trailing zeros, you just isolate this smallest bit and then you count the leading zeros and you subtract it from 255. So you don't need to implement this CTZ. It's a waste of opcode namespace. So CLZ is a very general mathematical operation. In math, it's used in log2, square root, cube root. A lot of sublinear functions, you can use CLZ as a way to find the initial approximation and then you refine it from there. For square root, you can use CLZ to find a log2 in constant time, maybe a few opcodes. Then you use some Newton-Raphson to converge to a nicer result. It's used in data structures like bitmaps, skip these. I heard more and more CLOBs, like order book on chain, they like to use bitmaps. So maybe CLZ will make their life faster. It's also used in some algorithms, like in Solidity we have a run length encoding compression. It uses CLZ. We have a string search which uses some form of CLZ too. And it's like you can find it everywhere once you recognize it. So for example, down here, this is Pascal's triangle, and if you represent it in binary form, it somehow produces this nice looking shape. And Vitalik, being the genius he is, he sees all this relationship like immediately. So he said, yeah, the logarithm, because the length of this binary string is essentially log2. It's a parabola. Yeah, so CLZ is like log2. You can just compute log2 with CLZ. And it's like used everywhere. You can see it everywhere. Once you see it, you can't unsee it. So why do we want to make it an opcode, even though we can emulate it today? You can make it very cheap to compute, like 63 times cheaper compared to the most efficient Solidity code right now. It's cheaper to prove for SP1. I will argue that it's more than 63 times cheaper. And of course, you get a smaller bytecode. Why you get smaller bytecode? Okay, later I will show you. Because the way CLZ is implemented today, we use quite a lot of giant magic constants. And all these magic constants, they occupy a lot of bytecode space. So there are some considerations why I propose this opcode. One is stateless. you can understand the course, you can profile the course very well, and it's very easy to implement. So back then at Interop in Berlin, well, after the first day, I think everyone implemented it in just like one day. So CLZ is available in most modern processors, and I believe that we can learn a lot from how all these modern processors evolve. Because if you look at a modern processor, they also face the same constraints as the EVM. You can only implement so many opcodes on a modern processor, and therefore you want to select the most useful opcodes to be included. And CLZ is available in most of them. So because it's so universal, it hints to us that yes, this is a good opcode to include. So I would say it's one of, if not the lowest hanging fruit we can implement today to speed up the EVM. As in the computation, not state access. State access is the main bottleneck, but for the computation part, I think CLZ is one of the lowest hanging fruit. You can have maximum impact with just one opcode. Okay, so the initial idea has been conceived way back in 2022. If you view the forums post on Ethereum Magicians, it's all the way back in September 11. But then I didn't have the motivation to push it because I asked about, people say to get an opcode into mainnet, you have to implement in all the clients. You have to get a lot of support here and there, which is very difficult. So I thought, okay, maybe considering the difficulty and everything, maybe it's not time yet. But then after I maintained Solidity and build up Solidity more and more, I realized that there are too many places where CLZ appears. So after EOF has been removed from Fusaka, people are like, so the idea is like EOF makes the execution part faster. And without EOF, how can we make things faster? Why not just implement one CLZ opcode since it's everywhere? So a few days after, I quickly draft out 7939 CLZ, went to Berlin and convinced everyone to implement it. And somehow by sheer luck and community support, very strong community support, CLZ is selected for inclusion for Fusaka. And I'm very thankful for all the people who supported this opcode. Okay, so right now today, if you want to implement CLZ, you have to do this chunk of code. It's quite intimidating looking, it's quite scary looking. And I would say these crazy magic numbers down here, there's a way to find them. I use something called the Z3 solver in Python to find them. This stuff is like 184 gas. CLZ opcode is like 3 gas. So 184 divided by 3, around, I think 63 or 64. Yeah, that's how I approximated it to be 64 times speed up. So these implementation, I think Uniswap V4 use it. Most people who use Bitmap, they also will use it because it's like, you can only get so fast. This is the fastest you can get today. And it has been like formally verified. So yeah, you probably want to use it. So there are a few variants of CLZ. There are some areas where you don't need like the full precision of CLZ. Maybe you just want to use CLZ to count the number of leading 0 bytes. You can use this. So this is a specialized variant of CLZ. In CD compress, we want to count the number of leading 0 bytes. We do all this magic down here. And the thing about specializing CLZ is that each time we specialize, we have to compute new magic constants for it. And this leads to more work and also a risk, a possibility that you can introduce bugs because you have to find new magic constants. So in another location in Solidity, we have another variant of CLZ. Somehow this constant, I did some magic so that this lookup is essentially this magic thing down here. Yeah. So I adjust the magic constant so that I can shortcut some operations. And for square root, you don't need the full precision of CLZ. You can do an approximate version and let the Newton-Raphson somehow correct the results. You just need a good enough approximation. So different areas, we specialize CLZ differently. And all these like it looks cool, but in the end, you could have one simple opcode to replace all of them. So let's say we have CLZ tomorrow. Well, so lady might not have the flexing power anymore because all these easy math can be they can be replaced by a single opcode. So I'm sort of like saying, okay, I give up my flex for the back so that everyone can be faster. And also sometimes we tend to avoid algorithms because they need to use CLZ. So for example, if you can think of some algorithm that use CLZ. So right now CLZ costs 184 gas, I think, and you need to repeat it many times. You will be like, okay, this is expensive because you use CLZ. Maybe I will use some other suboptimal algorithms that doesn't have CLZ because it's just so difficult to implement CLZ in EVM today. So next time, we won't have this restriction anymore. We won't be restricted to some algorithms just because of the essence of this opcode. And finally, I believe it can make compilers perform better. Like for example, if you go back to this giant chunk of code, the compiler might have some difficulty inlining this, although this is completely branchless, because all these constants are quite big. It occupies a lot of space if you inline it here and there. So the compiler might choose to not inline this function. And if it's just one opcode, the compiler can inline it very easily, very trivially, and it can therefore optimize it easier. Because if you inline the big chunk of code previously, the compiler need to find out what is the stack ordering such that the stack operations are minimal. They have to shuffle the stack, all this weird stuff. So if you have one opcode, you don't need to like do all this stack shuffling to optimize the code. It's just one opcode. So your compiler will have an easier time to inline and optimize. So your compilation time might be faster. So to implement a CLZ, you can do it in a very SP1 friendly way. So right now, I think to prove the EVM, most people, I think the cutting edge is SP. So ref is compilable to SP1, the RV32IM subset, and SP1 can prove it. So the idea is that instead of, so previously we have all those giant opcodes here and there, all those giant constants and all those like fancy math in the application layer, but now we push it to the native layer. And because we push everything to the client layer instead of the application layer, you can avoid some operations that are not very ZK friendly. I intentionally wrote it using branching code instead of SIMD because this makes it easier to compile for RV32IM. And also, once it compiles to RV32IM, it's faster if you have branching code. And also, this implementation doesn't use any dynamic right shifts, which is one of the most expensive operations in SP1. If you implement it this way, it's quite fast for regular compute, as fast as the regular 256-bit add. So it's fast for regular compute, but for SP1 proving, it's actually faster, cheaper than add. Yeah, so if you look at the table of SP1 RV32IM cost, you'll find that shift right is very expensive. And if we want to go use this thing to compute CLZ, you see all this shift right. This is going to be a headache for SP1. Yep. So we make it native, we avoid all the shift right. It becomes much easier to prove. So I anticipate that compilers can support this on day one because we have, in the past, Solidity has supported like push 0 on day one. And I think transient storage on day one. So I think it's possible. This is like a single opcode with a single operand, like transient storage. Wait, I think transient storage, yeah, T-load also has a single operand. So we know what to do to implement, to support it. The thing is L2s, maybe L2s will take a few months to catch up because some L2s do a lot of customization here and there. So pulling from the mainnet clients maybe they need a few months to merge everything. Yep, I think that's it about CLZ, and hopefully in the upcoming months to years, the problem of fully utilizing all the 256 bits of the EVM will not be that much of a hassle anymore.
Thank you for sharing this. I was really interested to learn about your motivation, like why you make this push after EOF is out of Fusaka, but you very well explained that. And your story for going to Berlin and convincing developer to implement this in client is pretty interesting. I am happy that things worked out. We don't think that EVM is dead. There would be proposals which would be coming up to support, and there are certain proposals which are helping the present developer community as well. Once again, thank you so much for sharing this presentation. I do have a few follow-up questions. If you're fine, we can perhaps go ahead with that.
Okay, let's go.
All right. So you are proposing the CLZ as a native opcode. I'm wondering why you just did not leave it for compiler. You mentioned that Solidity and Viper compiler will be compatible from day one. Do we really need to have this as a native opcode?
Okay, so back then in the very ancient days, there is no shift left and shift right in the EVM. And people have to emulate shift left and shift right using multiplication. And it's actually very tedious to do that and expensive. So they introduced shift left and shift right opcode. I think for CLZ it's even worse because it's not just a simple multiplication. You have to do all these crazy acrobatics just to count the leading zeros. So yeah, you can do this today. It costs 184 gas. But if your algorithm needs to implement this in the loop, you're going to rake up a lot of gas.
That is interesting. You already have explained that it makes things cheaper, argued for 16 times cheaper. Wonder, does having a native CLZ also makes things safer?
It also makes I think it will make things safer because right now, low level developers like me, we like to flex our bitwise techniques by creating variants of CLZ. And all these constants, we have to use this thing called Z3 to hunt for all these constants for each specific case. And if a developer doesn't know how to do that, okay, I think the developer should know how to do that. But anyway, it introduced more effort and room for error. What if they forgot to update a magic constant? Yeah, something like that.
Yeah, sure. Decreasing the room for error will definitely make the code more safer. Well, my next question is with respect to gas and performance. In the proposal, you have mentioned or proposed a gas cost for CLZ. I wonder, how did you benchmark this? Maybe you can talk a little about the proposed gas cost.
Okay, so today there's an opcode called add. Add is, let me see. Add takes in A and B, A plus B, two operands, and it costs 3 gas. So CLZ takes in one operand, and that's so one operand should be cheaper because every time you take in an operand, you have to pop things from the stack. The EVM emulator has to do more operations. So yeah, one operand is cheaper than 2 operands. And okay, let's say we ignore all the overheads of the operand popping the operands. How fast is CLZ? Just for regular compute. So we implement this. We implement like some kind of dumb program to do 1 million X, some dumb program to do 1 million CLZ, and we time it. And both of them took approximately the same amount of time, like 17 seconds versus 19 seconds. CLZ is slightly slower, like 19 seconds compared to add. But it's not like if CLZ is say 30 seconds, then maybe I will propose a gas cost of 5. But because it's so close to the runtime of add, I think a reasonable gas cost is 3.
All right. And just trying to understand this better. So when we are comparing with any other opcodes like ADD or MUL, this gas cost that we are having it for CLZ, it makes it cheaper. That's why we have this proposal. Is that a correct
Yes.
understanding of it? Okay.
Yes.
I noticed a conversation in Fellowship of Ethereum Magician where a developer suggests that when we are using gas cost of CLZ with respect to any other proposal, I think he mentioned a particular EIP-7904, which is general repricing, is suggesting the gas cost should be 1. So do you suggest that the gas cost proposed with this proposal should not be a fixed value, but it can be a range?
Okay, I think in the future, if somehow all the opcodes are repriced to 1 gas, all the arithmetic opcodes are just 1 gas, CLZ will definitely be 1 gas. But there's one opcode I'm a bit worried about, which is shift right. Shift right is very unfriendly for SP1. Maybe shift right need to cost 2 gas if we reprice everything. But that's just my 2 cents. Maybe further benchmarking can give tighter bounds, and maybe we can safely put everything as 1 gas. Maybe we can do that. But basically, to decide on a safe bound, we just have to benchmark everything in the future again. But for now, 3 gas is a safe bound for SP1. No, for CLZ. Even considering ZK proving, it should be cheaper in SP1.
Yeah, sure. I mean, it's good to have a safe bound, and we can perhaps continue more optimization research, and we can come up with other variants of it in upcoming EIPs if needed. Well, we know that this proposal is now considered for Fusaka. You did talk about your story for going to convince each client team collecting feedback for the proposal.
Okay, it almost didn't get into Fusaka because by the time I wrote the EIP, I drafted the EIP, it was already past the deadline for consideration. So I have to really convince everyone. But because it's so easy to implement, like everyone implemented it in a day. But if you sit beside them and you see them actually implementing it, maybe it's just like 15 minutes and it's done.
I mean, I would say you became very lucky here, or the proposal is like
Yes.
really, really trivial that people have accepted it, because at this point we generally see proposal going out, not getting in.
Yeah, I think I'm very happy that the Ethereum core developers community, all the client teams are very pragmatic. Okay, so the thing about EIPs these days is that they are, I would say, getting more and more complicated because all the low-hanging fruits have been already eaten up. And CLZ is one of the remaining low-hanging fruits that can be just sneaked in an afternoon's work. So I think this is one of the last few low-hanging fruits that we can find. And luckily, I'm so glad that they included this in Fusaka, because if it's going to Amsterdam, it will be bottlenecked by all the other heavy EIPs that are aiming for Amsterdam. And wow, the EIPs for Amsterdam are, I would say, non-trivial.
Right, very true. Well, at this stage, I hope the answer is no, but still, I have to ask my question. Do you see any blocker or any open question that needs to be answered before this proposal is moved forward with the AIP process?
I think we have profiled it. We have made the spam test net to make sure that this doesn't open up any DDoS risk. So I think everything is ironed out. Just go ahead. I think Solidity maybe implement it, because there might be some code base that have a function called CLZ. It might clash with some existing code bases if they have CLZ as a global identifier. Yeah, but other than this, so the two adoption issues is that maybe it might break some existing code base, but highly unlikely because CLZ is such a low level of codes. Only optimizers and like very low level math experts will need to touch it. But it's used everywhere. And I think L2s maybe they will take a few months to catch up, so there might be some fragmentation, but in the end, like T-Store, we have maybe 6 or 7 months where everybody is fragmented here and there, but eventually everybody supported T-Store, transient storage. Yeah, I think maybe in 2026 June, probably you can use it everywhere.
That's good to know. Well, when we are talking about the use case, I'm wondering, outside the DevNet testing, are you by any chance aware of any real contract or tool which either is already using this proposal or is going to be benefited from this opcode?
So the thing about opcode is that mainnet has to go first. This is for pre-compiles, L2s can go first. But for opcodes, once a compiler supports it, you can't conditionally disable the support, say, for certain networks. Solidity doesn't support conditional disabling of opcodes. So if you want to introduce an opcode, mainnet has to go first. So right now, no code base out there has CLZ, uses CLZ as a native opcode. Yeah, there isn't any L2 that uses CLZ right now. Mainnet has to go first.
Yeah, and thank you for sharing this very good difference between the opcode and the pre-compile. Like, opcode is definitely dependent upon the mainnet. Before that, projects may not be able to use it. Well, my next question is with respect to proposal status. We notice that the proposal is currently in review status, which is fair because this is a relatively new proposal and you are still working on it. But because this has already been SFI, it is eligible to go to the review status. But it depends upon the author, and like if there is a set of co-authors, they can decide on it if this is ready, or are you expecting any changes before this can be moved to the review status?
I think, yeah, I have to make a PR to move it to review status. So right now, I think I have to, maybe I will clarify like some grammar maybe some awkward phrasing in the EIP. It's mostly like editorial issues because like people are confident about the course and everything else. So it's more of like tidying up the EIP before we get ready for review, then last call then final. Maybe there's no last call for EIPs. Yeah.
That depends upon the stages. When the proposal will move to the public testnet, then it will become last call. But for now, you can rest in review status.
Yeah, I make PR to pump it to review.
Whenever you are ready, please feel free to make a PR and we should see the proposal in review status. Okay. Well, that concluded all the questions which were with respect to the proposal. I do have a set of rapid fire round. We want to have these questions answered in one word, one sentence, phrases as small as possible. So are you ready for it?
Okay, let's go.
What's one EIP you wish more people paid attention to?
Gas to ETH. I forgot the number. It's by Charles Cooper, the Viper maintainer.
My next question is, what is more fun to optimize, gas, zk-proof, or compiler internals?
I think gas, because you have freedom to invent new math.
And people love gas optimization. Well,
yes.
Thank you. What is one dev tool you can't live without?
Definitely Foundry.
Cool. What is your favorite thing about working on Ethereum?
The community really cares and is intellectually honest.
Right. We have a very good community here. If you could instantly ship one change to Ethereum, what would it be?
I think this has some overlaps with what is the most under considered EIP. I will immediately ship gas to ETH, but with a catch. 10% of the gas that is burned will go to the validators.
Mm-hmm.
People use the opcode to burn gas to convert to ETH, and everyone, all the validators helps the network earn more fees.
That's right. Well, if you have to say, what would you say is the most underrated opcode so far in Ethereum's history?
Mod. Multiply modulo. I think without implementing custom cryptography will be impossible. And it's used in quite a lot of fancy math.
Very well. My next question is EIP, you have changed your mind about recently. Like earlier you didn't like the proposal, now you like it, or earlier you liked the proposal but you don't like it anymore?
Yeah, CIF more. But EIP, I think I don't have much regrets on any EIPs. Wait. Hold on. I think there is one, but it's a written data copy. Yeah, so written data copy is proposed after stuff like core data copy has been proposed, and code copy, Xcode copy. So Xcode copy, code copy, core data copy, all of them have a very consistent behavior. When you copy out of bound bytes, any bytes that are out of bounds, it returns 0 for any out of bound bytes. And sometimes I abuse this behavior to a zeroized memory with very efficient, in the most efficient way as possible. But return data copy, if you copy any out of bound bytes, it reverts. It does an EVM revert. I think that is inconsistent. It also leads to some difficulties in implementing it in the compiler.
Thank you for that. And my last question for today is one word that describes your coding style.
Okay, I think it's a bit cheesy to say like it's formless. Like you imagine, okay, formless like Jikundo. You just do what is the most efficient way to get to the result, and you do it in a way that is somehow maintainable and also in a way that allows you to improvise and discover new optimizations easier.
Right, and everyone has different style. It's good to know how each person deal with it, like how they prefer it. Very well, that brings us to the end of today's episode. Huge thanks to Vectorized for joining us on PEEPanEIP and breaking down EIP-7939. If you want to dive deeper into this proposal, please check out the EIP as well as join the discussion on Ethereum Magician. Dear listeners, if you find this episode helpful, please share it with fellow Ethereum builders and users. Let us know which EIP you would like to cover in our next episode. Please check out description for ways to support our way. Until next time, keep learning, stay curious, and keep perfecting Ethereum. Cheers.